Hi Deepa, good to see you again.
Hi, good morning.
We've asked people to think about this question and enter their responses into the chat, and we'll just go over them in 3 or 4 minutes. Okay, so we've got 2 good ones so far. Arthur says x and x minus 1 to remove the low order set bit. You mean clear it? Clear
Yes.
yeah,
Yeah,
okay.
clear.
And do you remember using it in any context?
Well, you can use it to count the number of bits, or if you take that and then XOR it with the original X, that'll tell you which bit was set, so you can iterate over the bits that are set.
Okay.
In this way.
Cool. Jason says to square a number, shift left. That is very useful. So
I think
yeah,
I'm wrong about
definitely.
that, actually.
I'm
It's just
sorry?
multiply by 2, shift left, I think, not
Yeah,
squaring.
that's right. That's right.
Yeah.
Multiply
Well,
by
if the
2.
number happens to be 2.
Yeah.
Okay. I also, it's just this reflex that you have. You shift left, it means something you don't even read. Like, okay, the guy wrote square actually. But yeah. Miguel says, just came here to learn what shift left means, but did not get it. Yeah, we'll definitely have a chance to talk about it. Michael says, swap 2 bytes using XOR instead of temp variable. Would you explain how that would work? Do you remember how XOR is used? And is it really just 2 bytes or?
To exchange 2 bytes, you XOR one with the other, and then the other with the one, and then the one with the other again, and they end up swapping.
Nice. Arthur actually has a little chained assignment there.
Is that XOR? Yeah, that's it. That's exactly it. Yeah,
that's it. Very
that's
nice.
it. He knows.
Very nice. So
Yeah.
swapping 2 variable values, let's say ints, without using a temporary. So that is really cool. Because normally, what would you do? You would say, and we saw this in an exercise, right? And so you would create a temporary variable, assign it A, and then you would assign B to A, and then you would assign the temporary to B. Nice. Anything else? Anything that you remember from ever using bits or bitwise operations? Doesn't need to be a favorite. Okay, so these are really good. And the reason, I guess you know, why we're talking about this is because these are 2 sections that we're going to cover today bitwise operations and bytewise operations. Before we get to those two sections, there's a couple of earlier sections. So this is the agenda for today. For the most part, we will be reading through Fascicle 1, MX, which is the MMIX booklet, a separate booklet from TAOCP itself. And it has sort of the programmer-oriented introduction to MMIX, which is the computer that Knuth designed specifically for educational and purposes and for using in TAOCP. And but there is a little section, like half a page or a bit more, from volume 1, chapter 1, that we'll need. It's a little mathematical explanation of the div operation, so it'll be nice to have that discussed as well. So if you want to open both, if you have them both online or whatever format you have, you can just go ahead and do that right now. Otherwise, the slide will tell us when we need to switch between the two texts. So yeah, so let's get going. Welcome everyone to our 4th meetup. This is the Art of Computer Programming meetup, reading group meetup, and we will be studying and reading about basic MMIX instructions. So this is the second meetup on MMIX itself. The first one, which was last Saturday, we went over like the basic memory layout and just the very basic organization of MMIX instructions, their format, and we did see some examples of load and store instructions. MMIX is an example of a RISC style architecture, which is reduced instruction set computing, and there's two hallmarks of RISC architectures. One is that there is a uniformity to all of the instructions. They generally tend to be the same length in terms of bytes. They tend to have a very similar format in terms of the operator and the number of operands. And the other hallmark is that you tend not to have a lot of complicated instructions. So the idea is that you design just a set of relatively simple primitive operators that you can combine in various ways to do more complex operations. Anyone know why RISC may be a good idea? Like, what is the philosophy behind RISC?
Well, one of the philosophies I would say is, or one of the reasons that we move toward RISC and away from complex instruction sets like x86 is a move toward software compilers. Instead of people having to write assembly by hand and looking for those specific instructions that do exactly what the human wants to do, they would be designed so that the compiler could take high-level code and very easily map it down to whatever is made up of simple building blocks. There wouldn't be any clever tricks that the human would know that the software wouldn't know, which is ironic for this book.
How so?
Well, he's going to be writing a whole lot of assembly by hand. He's not going to be a compiler. So you may wish that he had instructions that did clever little things.
Michael says in the chat, each instruction executes in a single clock cycle. That's a goal. Like, that would be a goal of RISC, as opposed to some other style like CISC, complex instruction set computers, where obviously if they're complex instructions, that means you need to do a lot more work for each instruction, and so you couldn't really guarantee one instruction per one clock cycle. Why is that good though? Because in the end, like, why if you're doing a whole bunch of primitive instructions, each one takes a single clock cycle, but it adds up to a whole bunch of clock cycles versus one, could be like one complex instruction that's the equivalent of 10 primitive instructions, takes the same amount of time. Why would one be preferred over the other?
Well, the goal is to make the processor faster, and if it can do each instruction, even though they can be smaller, and they're not necessarily smaller. Like you have to have one instruction to load, and then another instruction to add, and then another instruction to store. But I don't think even a CISC can do load, add, and store all in the same. Well, actually, yeah, they do have that in an instruction, I guess, but it wouldn't put the intermediate in a register. It would be a little bit different, but it would take more. A load, add, and store is going to definitely take at least 2 clock cycles, because you're going to need 1 clock cycle to read it, 1 clock cycle to write it back, and really, in reality, it would probably take 3, because you need to add it, and you're not going to be able to do that while you're reading or while you're writing.
Would someone care to explain what a clock cycle is and why is it relevant to instructions or assembly machine level coding for those of us who may not be familiar with this, or may not remember? Like if you've been just programming software for a long time, you may have kind of forgotten this stuff. Michael, do you want to take a stab at it?
The CPU has a clock inside, which steps it through. It's a like when you see that your Pentium is 4 gigahertz, it means that the clock is going off 4 giga per second, 4 giga clock cycles per second. And in each of that clock cycle, the CPU can do one thing. Well, actually, I think a Pentium does a lot of things in a clock cycle because it does things in parallel. But like for instance, it can put an address. It can address a certain byte of memory, or which would cause that memory to be read. Or it can read the memory, or it can add 2 registers. Some things take more than 1 clock cycle, especially when you get to floating point. But the idea is every clock cycle puts the CPU through a step, and a step is actually something smaller than an instruction. So, like an instruction on a x86 to add a memory location to a particular register might actually take 3 clock cycles. 1 to put the address out on the address bus, 1 to read in the byte from memory that was addressed by what was on the address bus, and then a third one to add the 2 together. Probably even more than that.
So Miguel asks, you mean that it is actually hard to have a single instruction per cycle? Like that's a difficult goal to attain?
I don't know whether it's difficult. It's just a different design philosophy. Like if you want to try and if you want to try and optimize for instructions that are more powerful and therefore closer to what you would write in a higher level language, maybe you end up with CISC. And if you want to make things faster by actually, I think in a RISC case, they do. The goal is to do 1 instruction per clock cycle, but I think the clock cycles tend to be slower than on a Pentium.
Okay, so yeah, I mean, this is like we're digressing a little bit, but I do feel like, we are studying assembly language, machine level code. It would be nice to have at least a context as to why certain choices are being made, especially by Knuth. And I forgot another hallmark of RISC design. This is actually a very critical one, as opposed to like x86, which is an example of a complex instruction set computer. That is, every operation on data, like when you want to change data, that only takes place within registers. So you have to bring data from memory into registers, do some work on it, and then write it back to memory. So you cannot directly access memory. At least that's sort of the driving philosophy. One of the reasons from what I remember for sort of the popularity of RISC, or why RISC took off in the 1990s especially, was what's called instruction level parallelism. And this has to do with how instructions are actually being processed by the CPU. There's this, you can think of like a sequence of instructions that is flowing through a pipeline, one after the other. Of course, we know that code doesn't always execute sequentially, like the lines of code that you write. We're not just going through 1, 2, 3, 4, 5, 6, 7. Sometimes we go off to one side, and sometimes we loop. And but there are these pipelines, and they're being driven by these clock cycles. You know, like think of like a sewing machine operator, the old style, or a loom. You know, somebody presses a pedal and then something happens, the needle moves up and down. So it's sort of like that. A clock cycles is sort of driving what can be done by the CPU in a particular amount of time, and it's a very small amount of work. And with a uniform instruction length and very simple operands and operators and sort of this very predictable structure to each instruction, it turns out, or at least it turned out at that time, that you could make the pipelines a lot more efficient using some sort of parallelism. You could actually achieve, if I remember correctly, sub-clock cycle instructions. So you could, if I remember correctly, again, I may be wrong, you could overall, you could be running more than one instruction per clock cycle. But we'll save the discussion for another day. I'm sure it'll come up again. So this is going to be our agenda, and as I mentioned, we'll use both text today, a little bit from both, and just to recap our procedure, we just read a couple of pages at a time, just enough for 5 minutes. There'll be a slide saying what we're reading, where we're at. As you read, please enter comments and questions in the chat panel. And then one of us will recap the reading. I felt like that would be a nice way, especially for people who are watching the recording, to get sort of a summary of what we just read. And then we'll go over the comments and discuss the reading. And then I will be posting the entire chat as well as any other notes to our GitHub Meetings repo. And I've done that already for all the previous meetups, so I've caught up. We have been starting with a quote from Knuth. And today, what I'm going to do is actually play you a quote. So tell me if this is showing up. It should be a YouTube video. Cool. And now hopefully the sound will also go through.
Where both of the numbers were 1. And you also had OR, and you had exclusive OR, which is, in fact, at one point was a classified thing. I went to the, it was used so often in code breaking. I went to a conference in Los Alamos in 1976 where somebody wrote the truth table for exclusive OR on the blackboard, and the security man erased it immediately. Anyway, we can't keep it a secret, any longer. So now, okay. So
let's go back to our slides, and here's the quote.
for anyone not in on the joke, XOR is basically the not equals operation. True. If you have true and true XOR true, you get false, true XOR false. So.
Okay, so let's start our reading. We will begin with Fascicle 1. And we are reading section 131 prime, description of MMIX, the arithmetic operators piece, pages 8 through 9. We'll take about 7 minutes for this, so till about 2:30. Welcome, Yuri. We are reading the section that's on the slide till about 2:30. Okay, does anyone need more time? Right, so let us, would someone recap what we just read? If you can just paraphrase or summarize it.
There's a bunch of different operations for doing math in MMIX.
Yep. Any significant things that you felt kind of stood out that, need more attention?
He had a golden ratio special number that kind of seemed like not super important, but kind of interesting if I wanted to spend more time looking at that, figuring that out. A lot of the unsigned operations don't overflow, or I don't think any of them do. Yeah, and then the 2 ADDU, 4 ADDU, 8 and 16 for computing addresses also seemed like something I might need to figure out in detail a little bit later on at some point.
Yeah,
But
those are really great points. Anything else that stood out for like anyone else to respond or comment on, or any questions?
Sorry, I didn't hear the previous comment or question, but I am so I would like to know a little bit more of why these concatenations of the registers are happening, like the himult register and the dividend register. What's the point of that, and why with shift left and shift right, that means that we don't need those. I guess it's because the specific X have to have the specific settings, but still, so I don't. Those are my main confusions. Like, why are we having these weird registers, and what's the deal with shift left and shift right?
Okay, that is absolutely what I wanted somebody to bring up. Any answers for Miguel? Let's first take the himult register.
Well, for both multiplication and division, if you put in two 64-bit numbers or even like two any size numbers, you're going to get out that same amount of information, right? Either as a quotient and remainder or a double wide result, right? If I multiply 64,000 by 64,000, I get something that does not fit in 16 bits. It spills over into the high bits. And so I need somewhere to put those high bits. In MMIX, we've only got 3 operands to each instruction, X, Y, and Z. And so if we're multiplying X by Y, we can't actually fit the whole result into Z. We can fit the low order bits into Z, but then there's also the upper half. And so the solution, which is kind of a weird solution, I think, I mean, but it's weird in a way that is familiar, is just pick and hard code a register, with which he's calling himult, which is RH, I think. And we are just going to stuff the high bits into there. And so you can specify, I'm multiplying X by Y and I want the answer to go into register Z, but you can't specify where you want the high bits of the result to go. Those are always going to go into special register H, and if you want them, you'd better go get them before some other instruction overwrites them. This is also how it works on, well, it works even more like this on x86, where there's a multiply instruction that takes, I think, 2 arbitrary registers and multiplies them and puts the answer into the DX register and the AX register. You just don't get any choice about that. Those are the 2 registers it decides to use. So MX is giving you the little bit of flexibility to choose the low order register, but not the high order one is still hard coded to this magic special register H.
That's a great answer. Just one nitpick, which is that in sort of the terminology that Knuth is following, X is generally the destination, and Y and Z are the inputs often. So, but yeah, really in simple terms, let's say that you're multiplying 2 single-digit numbers. right? So 2 times 3 is 6, fits into one digit, right? But what about 4 times 4, 4 times 5? Then you need an extra digit for the second, digit that could potentially form. So the same thing with these registers. You've got two registers that you're multiplying. Both of them are 64 bits. The result could be it could require more than 64 bits. So where do you place those extra bits? And exactly as Arthur said, there's this fixed register. So I did go over some of these registers last weekend. They're called special registers. So each register has a very specific purpose, and they're separated from the general registers, of which there are 256. And those are just numbered from 0 to 255, and the notation is a $sign before them. So you would say $0 is register, general purpose register 0. But the special registers have these specific names. So RH is the high mult, or the high portion of a multiplication product register. So yeah, and we'll see examples of this after the break when we do the hands-on visual debugger. Anything else? Oh yeah, Miguel had a second question as well. What was that, Miguel? What was the second part?
Shift right, shift left. Yeah. So let me see if my intuition is anywhere near the reality. So I'm assuming that so my first intuition is you literally want to have this bit and move it in places to one side. The other is either maybe one bit or a chunk of bits from the byte or from a word. The other intuition is some sort of like abelian group that you just want to move the whole thing a little bit to the left or to the right, and things is like a circle, and the bit is just going to, the bit of the left is going to appear on the right if you move the whole thing. I'm not sure if I'm making sense.
That does make sense for people who would know what an abelian group is, but yeah, I think your intuition is pretty much there. Does someone just want to explain what a shift, what the idea behind a shift is, and whether it's a left or a right, what the impact is?
I would say you described two different operations there, right? And the first one is what's usually called a shift, and the second one sounds like a rotate, where you shift bits off the end and they come back on the other side. We usually call that a rotate, either a left rotate or right rotate.
Yeah, you're right, but it is a choice, right? I mean, you could say when you're shifting, so you've got a bit binary representation of a number, and you're like, okay, let's say we have 4 bits, right? So let's say we have 1 0 1 0 left to right. Now, if I shift 1 bit left, what happens to the 1 bit that's on the leftmost position? Does it just fall off the face of the earth? And so I end up with 0 1 0. But then what happens to the first position? What do I do there? So there's these choices that you can make, right? You can say, I'm going to shift in zeros from the left, and whatever happens zeros from the right, and whatever happens on the left, things just fall off. I'll just ignore them. Or you could say something like, oh, shifting that leftmost bit, it'll make it come back. I suppose somebody could say that that's a valid shift in their opinion, but these are choices.
Yeah, and that would be a misuse of the word shift. That would be a rotate. If people are using that operation, they should call it rotate, because that's what it is.
Yeah. That's right, but it is involving some kind of shift. So in that sense, like if you just go by intuition, I think these are very natural questions for anyone to ask who may not be familiar with how a term is actually used in programming. So yeah, I think great questions. Anything else? What about div? Anyone had problems with div or questions about div?
Well, I don't know if this is, well, I was going to say div by 0 sounds like it could be a problem. But he also hasn't really explained what is overflow. He said a couple of times when the assigned addition overflows, or assigned shift can overflow, assigned multiply can overflow, and it signals overflow. And I know from sort of background knowledge that this probably involves, I'm going to guess he's going to set, special register O to 1 or something like that. But he hasn't actually explained that in the text as far as I can tell. But that's familiar.
I think he does explain it earlier on, and we saw examples of this, but overflow, you're absolutely right. There is a special register. It's called the arithmetic status register, RA, and it has a bit for integer overflow. So that bit gets set. Overflow generally just means any operation that resulted in something that the result couldn't really be represented in the destination register. And we want to signal some issue with that. So I bring up div because to me, when I first read this, I was a little confused about the mod and how it's actually being defined here. And he does make a reference to section 1.24, and that's what we're going to read next, because I feel like that, to me at least, that clarified a lot of things, like what does he mean by the result of integer division and what is the remainder, how is it defined. So let's move on to, so this is now going to TAOCP, volume 1, chapter 1. So if you don't have that open, if you could open that to page 39, or if you don't have page numbers, then it's section 124, integer functions. And it's just a very small piece. We'll spend about 5 minutes on this. If anyone has questions about the location, please enter them in the chat and I will clarify. Okay, so would someone like to recap what we just read? Arthur, do you want to take a stab at it and then bring up your point as well?
Oh, I don't know if I want to take a stab at it, but certainly we were talking about the definition of remainder, and so if you have two things that you're saying, this is the quotient and this is the remainder, it should be true that quotient times divisor plus remainder equals dividend. That should always be a rule.
How is the remainder being defined here?
That is a question that displays my ignorance.
Okay,
Well,
so that to me is, yeah, it's not very clear. You have to kind of look at equations 1 and 2. You know, he has the 1 and then the 2 in the parentheses. And then he says, consequently, if y is greater than 0, then x mod y, which is the remainder, is between 0 and y. So the remainder is positive or 0 when y is greater than 0. But if y is negative, then x mod y is between 0 and y again. But remember, y is negative, so the remainder is also negative. Okay, and this may be different to what you have used remainder as before. Like mathematically, often remainders are always positive. So it's one interpretation of remainder. So that's all I'll say here. But it is important to, I think, know what his definition is, because that's what will happen in these operations. So he's given some examples, and you can try them out. We'll see a couple of examples that will clarify this, but to me, this was really significant in furthering my understanding of how the remainder works. Now, going back to Arthur's question, he says the DIVU instruction seems very weird. If the dividend is greater than 2 to the 64 times the divisor, we just put dividend over 2 to the 64 into the quotient register. That's not mathematically valid, right? Is it mechanically useful / convenient? So if I remember correctly, this is the case when the dividend is equal to or greater than the divisor, right? Isn't that the case that you're mentioning?
yes. It says, the top of page 9 for me. So the DIVU operation also takes the special input, the special register as input, RD, which is the high bits of the dividend, so that you can use it to divide a 128-bit number by a 64-bit number. But if you make the value in RD so big that the quotient will not fit into 64 bits, so if RD is greater than or equal to the divisor Z, then DIVU XYZ simply sets X to RD and our R to Y. And this case always arises when Z is 0.
Yeah, so I guess your question is, if I understand you correctly, is like, this is not going to work. We just don't have the capacity to represent the result. Why has Knuth chosen to set these two registers the way he has described them? Like, is there any benefit to this? And I don't have an answer to that. So I don't know why, but I think what he's doing is he's just setting some values that in some way denote, some exceptional situation. And I don't know if he could have set them to arbitrary values or these values. Maybe these values are then somehow usable later on. Like if there was a problem, you could, I'm not 100% sure, like, why is it these values? I haven't thought as much about it. If somebody has an answer, That would be great. We will see an example of this as well, by the way, in the practice session after the break. Okay. All right. So for the benefit of Alan, who just joined us, we actually are reading from Fascicle 1 MMIX, going over some instructions, but we did look at this little section in TAOCP where he gives the mathematical definition of the remainder and quotient when you're dividing integers. What's important to, I think, to realize is that the definition for integer division is given in terms of dividing real numbers, right? The floor and the ceiling, I don't know if he actually uses the ceiling in here, but the floor, for the floor to work, the division has to be done using the real number. Like you have to, like if you're dividing 3 by 2, these are integers, you have to divide them as 3.0 divided by 2.0 and you'll get 1.5, and then the floor of that is 1. Similarly, if you're dividing 3 by minus 2, then you will get minus 1.5. And what is the floor of minus 1.5?
-2.
Minus 2, exactly. So that's where, sort of the remainder starts to make sense. Okay, so let's go on to, go back to the Fascicle 1 booklet, and we are now reading about conditional instructions. So this is section 131 prime, page 10 of Fascicle 1. And we have about 5 minutes to about 2:57. Okay. Again, could somebody summarize what we just read?
Well, MX has these instructions that are similar to, again, I'm basing things on x86 because that's what I know, but x86 has conditional move instructions. Actually, a lot of RISC architectures, like I think ARM and PowerPC, also have conditional move. And his first set, he's calling them conditional set if, but it's basically what x86 would call conditional move, where you're saying if some property of y, then copy z into x, otherwise don't. So we might use these in an algorithm where we want to put some, so if y is odd, do this to x, otherwise do that to x. So we might unconditionally first do the one thing to x and then say, if y is odd, overwrite x with this other value. And then the other set here, the ZS instructions, are all conditional move, but zero it out first. So sort of set it to 0, but then if that condition of y, copy the value of z into x.
Right. What would be the main difference between the conditions, the C set and the Z set?
The C set, if the condition is not true, we just leave x's value alone.
That's right. So the Z's will always do something to the destination register, and the C instructions, they may leave the register alone. Arthur, do you also want to bring up your points that you made about you didn't like the CSEV mnemonic?
Yeah, a nice symmetrical way of describing what he means. He says, by the way, a register is negative if its leftmost bit is 1, and it's odd if its rightmost bit is 1. So that feels really symmetrical. It's nice. It explains a little bit to, again, someone with my x86 sensibilities. x86 has no idea about odd or even, and we're always having to mask and then test against 0 to find out what was the lower bit set. He builds that right in, and then he gives this sort of explanation or rationale for, well, yeah, we can test the leftmost bit with these instructions, and then I also provide instructions to test the rightmost bit in case you want to do that. But it also occurs to me, besides that he doesn't call it odd and not odd, he calls it odd and even, which is, it's English, but it's not symmetrical.
Okay.
The other thing that's weird, though, is that 0 is neither negative nor positive by his definition, but 0 is even by his definition. And so his symmetrical way of describing it is literally true, but it left out that little bit about negative. There are numbers that are not negative, but also not positive. There are no numbers that are not odd, but not even either.
Right. Every number is either odd or even, and 0 is even. I actually like odd and even because it's much more specific than saying not odd and not odd, but fair enough. I think that your critique is perfectly valid.
I have a
So,
comment on this odd even thing
yeah.
too. It seems like not the most useful operations ever, and they're easy to implement, so we threw them in. But if you were really trying to make a super simple instruction set, I don't know if you would want to include these condition set if odd and even instructions. I don't know.
I think that's a great point. Anyone want to respond to that? Defend Knuth's decision or agree with Jason? Either way.
He uses it later on. He uses that peculiar fact and also the peculiar fact that if you have an odd number and you're addressing something more than a byte, it strips off the lower order bit or the lower 2 order or whatever it needs to. So in essence, you get in one word, you get to store both an address and a flag, and he uses that later. You'll never find that in the real world, but he seemed to like it.
Yeah, I would also both defend the decision and agree that you never see this in the real world. But I think quite often you do see in the real world algorithms that want to know this information. Even the trick that I mentioned at the very beginning of like stripping off bits, right? If I have a bit set, I might want to just shift it down by one, and at every iteration, what's the low order bit? As I shift it down, what's the low order bit? And if I have a instruction that just gives me that, which I do here, that's pretty nice. I don't have to do a whole, we'll AND it with 1 and then ask if it was 0. I see this being very useful, but it's also true. It's not very risky. It's very much, oh yeah, I'm going to be hand coding a lot of assembly. I'm going to need this instruction.
Fair enough.
Yeah, go ahead.
Just responding. Good points. So yeah.
I think, Jason, you raised a really great topic here. I've been thinking about this because I don't know, how Michael got to those examples, maybe in his previous readings or he's reading ahead, but I have also been reading ahead a little bit, and I did find some examples of things that I didn't quite get, like the first time around. I would literally search for those instructions in the source code and all the examples and to see why he would do this. But this is something that struck me like very early on, that this is a very rare occurrence of a programmer designing a computer architecture. And I really don't think this has ever happened in the history of computing as such. I think that people who design computers generally came from a very, knowledgeable and experienced hardware background. And I think that's the case today. And I did say that I didn't know if Knuth had ever had any industry experience designing a computer. It turns out that he did. So I was reading just a few days ago that he, I think when he was a grad student at Caltech, he had a short stint at Burroughs Corporation, which used to make computers at the time. And he acted like a consultant between two teams. They were designing a new computer, and there was a team that was designing the computer, and there was a team that was implementing the design. And he was providing some sort of consulting to both teams. So he acted as a liaison between them. And that gave me a much stronger appreciation and respect for like his experience. But I do feel, just like Arthur has mentioned, a lot of these things seem very natural for programmers because odd and even is like all over the place. I can't even think of the number of times in my code where you're doing things based on whether something is odd or even. And having an instruction reflects, I think, that background, his programmer point of view. And it'll be really interesting for us to see how this ends up being used in the algorithms, because Knuth, if anything, he's very meticulous. He's not going to waste like precious bits for instructions. And so my own feeling right now is whatever concerns or like questions I may have, I'm willing to defer them till I start to see these things in action. So we are now at 3:06, so let's take a 10-minute break. And when we come back, we will be reading the next section, which is on bitwise operations. And then we'll try to wrap that up. Maybe there's another section after that. So hopefully it won't take too long. Then we can go through some practice. And if we have some time, we'll do some exercises. So please return around 3:16 and feel free to turn off your webcams and refill your coffee. See you. All right, we are back. And let's just go straight to the next section, which is 131 prime again, but the bitwise operations section in there, pages 10 through 11. Okay, so could somebody tell us what we just read?
There's a lot of operations for working with the individual bits in registers.
Yep, that's exactly what it is. The standard Boolean bit level operations plus some combinations like um, OR of a not or of a complement of some bits, and then not, and then he's got the truth tables for the and the or and the XOR operations. Any questions or comments on this?
this set of bitwise operations here is noteworthy to me for being complete. I think on x86, I think they've added things like NAND and NOR, but certainly I don't think there's an NXOR, which is basically equality on each bit. If this bit position of Y is the same as the bit position of X, then I want to store 1, otherwise I want to store 0.
Right, right. Yeah, it's very interesting. Yeah, go ahead.
And then at the top of page 11, the two extra weird so these are not, okay, so the one is bitwise, and he uses the word bitwise correctly, of course, because it's Knuth. So the MUX instruction is sort of a select based on the bits in RM for each given bit. If that bit of RM is 1, we choose that bit from Y. If it's 0, we choose it from Z, and we put each of those bits in. And so again, it uses a magic special register, which strikes me as odd, but there's nowhere else to put that extra input. It's a function of 3 inputs. And then the sideways add, I was trying to work this out in my head, and I think it works out. This is literally, if you have 2 64-bit numbers, Y and Z, and you turn them sideways, so that now you have 64 2-bit numbers with the high order bit in Z and the low order bit in Y. So you have a bunch of 2-bit numbers, 0, 0, and 1, 0, and 1, 1, and 0, 1, and all these different 2-bit numbers, and you add them all up, you'll get a up to 65-bit result. Wait, what are we doing with this? I've confused myself already. Yes, that and then that number goes into X. No. Something.
Yeah, those two are weird and unusual. I haven't myself gone to trying out the MUX yet. The sideways add seems interesting, and again, we'll have to see how this ends up being used. But the definitions seem pretty straightforward, right? Was there anything about the definitions that were confusing? Like a lot of the other instructions do have, overflow or some other divide check that's happening and things like that, or the division definition of remainder. But here, is there anything that people needed some clarification on? Yuri says the AND N and the OR N seem non-RISC like. Because of the embedded inverse. Right, so every this kind of goes back to what Miguel was asking, like if one instruction that seems similar to another instruction could be possibly implemented in terms of the other instructions. And I think the idea behind RISC is that the answer would be no in general. The idea is that, every one of these instructions, how it's going to be implemented in the electronics, in the microarchitecture, and there would be some electronic combination of electronic components and transistors and things like that that sort of are used to combined in a certain way to implement a certain instruction, because that's the idea. Like you want that efficiency at the instruction level. If you're using some other instruction, then that's not really that efficient for you to be wasting an instruction on something that could be done by using other instructions pretty easily. So the application could do that, but that's sort of my take on it. Okay, so let's go on to the next section, which is bytewise operations, pages 11 through 12. And again, we have about 5 minutes till about 3:30. Okay. Could someone summarize?
Sure,
Jason, do you want to try? Oh, Arthur is unmuted, so let's
I'll
hear.
give it a shot again.
Okay.
So these are basic, well, it sort of opens thinking, okay, here are going to be the vector operations, vectorized operations, where we have, instead of saying we have a 64-bit integer, we're going to say, really, these 64 bits are grouped together, and we have two 32-bit integers, or four 16-bit integers, or, wait, did I? 8 1-byte integers, right. But the only operation he actually defines on the vector here is subtraction, and not just subtraction, but saturating subtraction.
Which is, how would you understand that or define or explain that?
Subtract z from y, but if that gives you a negative number, just clamp it to 0.
Yeah.
Don't allow it to go below 0. And so you could use this for masking. It's sort of like a bit mask, where you're saying, I want to just AND with this mask, which clears out all these bits. But here you're saying, I want to subtract this mask, which will decrement these values somewhat, and might send them to 0. Or might send them closer to 0. And he says this has some graphics applications. I haven't looked at the exercises yet, but apparently there's a bunch of exercises on these. But I thought it was interesting. There's no dot plus, there's no dot time, just minus is the one thing.
Yuri has a comment. For each bit, if y is 1 and z is 0, then x is 1. That seems like the input to the sideways add. Seems like the input to the sideways add. The sideways add counts the number of bit positions in which register y has a 1 and register z has a 0. Yeah, I can see the reasoning behind that. Michael asks, what would dot plus or dot times do? What are you referring to, Michael? Are you referring to the more and the matrix?
I'm referring to what Arthur said above. He said y dot plus, but y dot minus, but no dot plus or dot times.
Oh, you're calling that the dot minus. Yeah. I see. Yeah, so again, I guess it just depends on what has, in his opinion, is useful in terms of certain applications, and he's given some examples. So maybe there aren't as many good examples for a dot plus, and also because with dot minus, it kind of makes sense because negative has some significance. With a dot plus, how would you define it? By the way, this operation, I believe, is called the monus. So it has a lot of other applications. But a dot plus, I'm not sure if that has a name. Or yeah.
He called it monus.
Maybe that's why he didn't include it, because the SAD mnemonic used on actual hardware is taken by his sideways add. So he has nothing for saturated add.
Saturated add, right. Cool. Okay, so any opinions or thoughts on the matrix, the two matrix instructions? This is really unusual.
Yeah.
To the extent
to
the extent that I don't think this has ever been done in any architecture, or anything close to it has ever been. That's my opinion. But go ahead, Michael. Did you have something to say, or Miguel?
Miguel, yeah. I was trying to get intuition about what's supposed to be happening here. So you're multiplying these two matrices, right? So the matrices, the whole 64-bit or whatever divided in chunks, right? So the first 8 bits is the first row of the column or the matrix. The next 8 is the next row, and so on, so on, right? So you have two square matrices possibly, where the rows are the consecutive chunks of bits. So if you multiply them both, or the traverse doesn't matter. So if you traverse both, in any case, you are taking one of the consecutive bits and multiplying them and doing this weird dot product with the not consecutive one, right? Like the first ones of each of the chunks. And that's something. So what is happening? I don't like. I can see the operation, but I don't know why that mattered at all. Like why would you do that?
Any other ideas from somebody or comments, thoughts? Could somebody just maybe remind us how matrix multiplication works? Just standard matrix multiplication.
I can do it.
Yeah.
So basically, you take the first column of the right, you have one matrix to the left, one to the right. So you take the first column.
Just call them A and B.
Right.
Multiplying A and B.
Sure. Yeah, the first column of B, and you do a dot product with the first row of A, right? So you take the first element of the first column of B, the first element of the first row of A, and you multiply them and add them with the second and the second, and the third with each one, and that gives you a number, and that number goes to the first cell of the resulting matrix.
So you're kind of going like this, right?
Yeah.
So.
And in this case, what I was saying, the way I see it is, when you have the other matrix, when I see the transpose matrix, where each column is a consecutive byte or bit or word, then each of the first row is actually the first bit of each of the chunks, right? And then you're taking the first bit of each of the chunks, and you're combining them with the first chunk of the other octa, and that gives you a 1 or 0. It's totally random to me. Maybe it's not. Hopefully it's not. But for me, I don't see any.
I don't think that you would be the first one to say this, because as I said, nobody has ever done this, and there's a very good reason why nobody had ever done this before. Like, say up to the year 2000 or early 90s. What would that reason be? We didn't have 64-bit computers. Like, they weren't common before, let's say, 2000. Like, we did have 64-bit architectures in the 1990s, but that's kind of the time that they came out. And that's what's special about 64 bits, that you can form this 8x8 matrix of bits. And so nobody would have thought of this even before 64 bits, 64-bit computers. And I think that Knuth is really onto something here, but I think it's going to take a while for people to realize his sort of his proposal. One reason why I think this is very interesting. By the way, I did a search for this more in MXOR. There was a GitHub issue opened for WebAssembly. So WebAssembly, in case somebody doesn't know, is this sort of byte level representation. It's not quite a bytecode representation, but it's something like that, something similar, of some compiled language, let's say C or C++, typically C++ right now, and it can run in the browser under a JavaScript engine. So this is now standard. So it allows C++ compiled programs to be run in Chrome or any other browser. So WebAssembly, there was an issue opened by, I think, one of the guys who's involved in WebAssembly, and he said, can we think about supporting these two operations, the MOR and the MXOR. I don't think that they are seriously considering that right now, but it was interesting to see it being brought up in that context. One thing that really that struck me is there is this somewhat recent idea of using matrix operations to do graph operations. Operations on a graph being a representation of nodes and vertices, you know, like you have a network graph or graph of anything of nodes that are connected by edges. And there is now a library which is called GraphBLAS. It's a library and sort of a standard collection of ways to do graph problems and graph algorithms using matrix operations. And supposedly this is really efficient when you are dealing with really, really big graphs that are relatively empty, in the sense that not every node is connected to every node. So these would be represented as sparse matrices. And what's interesting about GraphBLAS is that when you try to understand it, they are talking about these very operations that Knuth is talking about, the generalized dot product, not the standard matrix dot product, but using the same kind of this multiply and add, where the multiplication operation and the addition are something else. So these are operations on what's called, I think, a generalized semi-ring. And so you can define different kinds of operations. The multiplication doesn't have to be like numeric multiplication, and the addition doesn't have to be like numeric addition. It can be something else. And based on how you define or how you choose the multiplication and the addition, you get different ways that you can use that kind of arithmetic or that multiplication to solve different problems. So I don't know enough about it to really discuss it, but that's what came to me like right away. I was so struck by that parallel. But it's very interesting, these operations. And again, it's only because we have 64, this is a 64-bit architecture, that this is even possible. Arthur says the original MIX didn't have 64-bit registers. Its registers were much weirder. Yeah, I think the original MIX, I didn't spend too much time on it. The thing that threw me off right away was, I seem to remember it was like a 6-bit word.
I forget all the details, but I know that it was a an underspecified architecture where it might be binary or it might be decimal.
Yeah, I think that's
went out of its way to not really say which was which, and then like to show that for certain operations it didn't matter, and then for other ones it did, and there were whole exercises about converting between binary and decimal, like for anyone who doesn't know, I mean literally a decimal computer, right? Like maybe it's a decimal computer. Let's have some weird.
So that was in response to Yuri's question, did the original MIX not have this instruction? Yeah, so as I said, it wouldn't really make sense for anything. I think the next time you could do this would be, let's see, 8x8, what would make sense? If you had a 9x9, although that doesn't sound as nice, but you know, something like that. But 8x8 is really nice, especially in terms of the definition of a byte being 8 bits.
There were some machines back in the day that were 36-bit, so you could have a 6x6.
6x6, yeah.
And do something with that.
Yeah, but again, 6 doesn't, at least from a programmer's point of view, it's not as nice a number. It's not a power of 2. But yeah, so very, very interesting stuff. And again, I just keep getting really impressed, is my term that I would use, by just how much of his programmer experience. Remember that he designed this thing in the early 90s. This is after like 30 or 35 years of TAOCP and all his experience and all his contributions to algorithms and programming. I mean, he's written a whole lot of programs and open sourced them. So, you know, he's bringing a lot of knowledge and experience to the table from a software and a programming point of view. So, yeah, I'm really impressed by that so far. Okay, so any other comments before we go to the visual debugger and see some arithmetic operations in action? All right, so I'm gonna switch over to the debugger. Okay, how does that look in terms of the font size and clarity? Looks fine. Okay, great. So in case you missed last week's demo, this is the MMIX visual debugger, and you know, I've provided links to where you can get this. It is free, it is open source, and I'm running it on Windows, but they're supposed to have binaries for Mac and Linux as well. So the way it works is that it essentially runs MMIX assembly language programs in a simulator that Knuth actually wrote, using an assembler that Knuth also wrote, but I think other people contributed to both projects later on. And so it's running on top of those, simulator and the assembler. The assembler takes your assembly language program and then generates a binary object file that is handed to the simulator. The simulator then runs it. And this visual debugger, which is a project that's maintained by Martin Ruckert, who's the author of the MMIX supplement, is you know, it adds this GUI on top of those things, but it works pretty well. There's a couple of minor annoyances that I found, but you know, I'm totally willing to ignore them because this is a great thing just to try these programs out. So let me post the link. I did post a link to the file or the program that we're using, but I'm going to paste it again in the chat in case you want to have a look at it directly. Previous week's program was called loadstore.mms. This is called arithmetic.mms. And let me load it. So I'll just say a few words again for those who missed last week about the program and the assembly language format. So comments, a comment line can begin with any non-alpha numeric character. There's a typo in alphanumeric. But try to avoid using a semicolon, pound sign, or white space because it can have some other effects that you may not realize. So, but yeah, technically you can start with any non-alphanumeric character. There's no multi-line comments. The trailing part of a line after a statement is ignored, so you can put inline comments that way. And when this file, this MMS file, let me just scroll down to show you the different lines. When this file is assembled, the object file is generated and then given to the simulator to run, that binary, the program, is loaded at memory address 0. So you start out at 0 unless you change it. So there are explicit directives for you to change the location, but the default is 0. So all I've done is I've gone over a whole bunch of these instructions and examples, and so the program doesn't actually do anything. These are just sample instructions. Okay, so there's a whole bunch of these there. And so what's happening in the beginning? In the beginning, I've got some of these assembler or assembly language directives. So these are not, strictly speaking, MMIX instructions. So in the MMIX assembly language, you have some extra pseudo operations, as Knuth calls them, available to you. So tetra, for example, says, I want this tetra or 4-byte value to be placed at memory, wherever you are in memory at that point. So since we started at 0, and since this is the first directive, it's going to be placed at address 0. And then I've got another tetra on line 24. That's going to place a 7. And since the first one took 4 bytes, this will go starting at address 4. So then I've got another tetra, a third tetra, which is a -5 in 2's complement. Then I've got some octas, and that's about it. So like there's 3 octas or 3 tetras, and we'll perform some arithmetic on these things. So they're taking up some space in memory, and then right after these sort of values that I've placed into memory as data, there's the first instruction at line 67. And there's some comments about what is going to happen when the code starts to run. So the registers, mostly, pretty much all of them are 0 to start out, except for 2. So register 0 is argc, which is the number of command line arguments. Register 1 is the address of argv, which is the array of command line argument strings. 255 is special. It's the first global register, and it will be non-zero, but you don't need to be concerned with using it right now. This is a very artificially constructed program, right? It doesn't do anything useful, so I'm running it without a command line. So what's going to happen is that argc will be 0 in this case, but this is very abnormal. Right? Normally, you run a program from a command line, and so then you at least have one argument, which is the program name itself. So argc would normally be at least 1, and then argv will not be empty normally, but in this case it is. So this had thrown me off like last week, and like, why is this exactly happening? And so I figured that out. Instructions, as we know, are 4 bytes. Make sure that the commas between the operands, you don't put any spaces, because that will be a syntax error. And that's about it. So a symbol main is required. That's the first line of the program that will actually run. So wherever you say is main, that's a label or a symbol associated with an instruction. And you can give any instruction, any name. Everything is case sensitive. So this particular name has to be written this way. All right, so what is our first instruction here? We have a load tetra, right? So it's going to take, remember, the first operand is the destination. So the next 2 are the inputs. In this case, I'm using an immediate, a constant in the third operand. We haven't read about this yet, but it's very easy to understand. So instead of a register number for certain instructions, you can give a constant. Remember that it's 1 byte. So the maximum you can give is, FF or 255. It is an unsigned byte, treated as an unsigned byte. So if you have some small number, you don't need to put it into a register and then use it. You can, for many instructions, you can just use that number right away. The pound sign is, of course, for hex, as we've read, but I could have just given a 0 there. That would be a decimal 0. And for addresses, I tend to use hex, but if it's like a number value that I'm going to use as a number, then you can just use decimal. These are my conventions, so you can do anything. All right, so let's run this. So the MMIX menu over here has the debugger choices, very standard debugger operations. And then there's some options for different things. You can go over these. I did go over them in last week's session, so you can look at that video also, try things out for yourself. Then there's a toolbar here that has, these are the debugging icons and buttons. So this is the debug and continue, which essentially starts the program and runs it to the end if you don't stop it. Next to it is a step instruction, which allows you to go over one instruction at a time. Okay, so let's do this. So I'm gonna do the debug and continue. I think I should check. You should always, you don't have to because it'll tell you if something is wrong, but in the sources, yeah. In the sources menu, there is this tab for the file. You should make sure that these two things are checked. Sometimes when you open a new file, these two things are not automatically checked. So it won't actually assemble and load your program. So you have to keep these checked. Then a red dot appears, which means you're good to go. Say OK. I hit debug continue, and you'll see what happens. Oh, what happened? Okay, here we go. So a whole bunch of panels appear. This black background panel I call a status panel that has some information about the registers and the operation that just ran the instruction. We're not going to look at this. I'm going to close this. These three bottom panels are memory panels. They show different segments of memory. This is the bottommost panel shows what's called the pool segment that has sort of the dynamically allocated storage area. And you can see that this address, this is actually argv. Sorry, this is not the pool segment, but the hex 40000, that's the pool segment. This is not being shown here. It's not going to be of interest to us right now because we don't have any command line arguments. But if you went to this address and looked at what's there right now, it would be empty. For a normal command line program, there would be strings there. So I'm going to close this. You close a panel by double clicking on the X, not a single click. It has to be a double click. Okay, close that. The 2 followed by zeros, this is called the data segment. This is where you can write data. You can't write data below this address. We're not going to be writing data in this program. Everything will be happening in registers, so I'm going to close this as well. Now this one, which is starting out at address 0, you can see that this has a whole bunch of stuff in there. And you can actually see what happened when the program was loaded. So if you look at that first directive, which was a tetra 3 to be placed, let me change the unit of display from octa to tetra. And here, now you can see at address 0, there's a 3. Address, that's 4 bytes. So address 4, that's a 7. Then followed by a -5, followed by zeros. Does anyone remember why this tetra is 0?
The next one you loaded, yeah, byte alignment was
Yeah,
it was
exactly.
8.
It's the alignment. because the next directive was for an octa to be loaded into memory. An octa can only be loaded at an address that is a multiple of 8. And this particular address is not a multiple of 8. So it's skipped, and then the next valid address is where the octa gets loaded. And if I change the unit from tetra back to octa, you can see that this is the octa that we wanted, and then followed by the octa over here. And these values are somewhat interesting because this one, number 30, line 34, this is the largest signed number. Remember, these are just bits in memory. So, you know, signed, unsigned is how we use them, but I plan to use it as the largest signed number. And so that's why I had this value in there. And similarly, this is the smallest signed number, -2 to the 63. So, and then that's followed by the largest unsigned number, which is 2 to the 64 minus 1. That's all ones. And that's placed in memory as well. So now that I've got these values in memory, let's start running through the instructions. So, and by the way, you can switch the display format, the numeric format, from hex to characters. We're not dealing with strings, so this is not interesting. But if you wanted an unsigned value, you could, you know, look at the unsigned value for this octa. You can look at the signed value for the octa, and then you can look at, this is not interesting to us either. If you did have floating point values, then you could do this. And this is essentially the bits in there. Okay, let me close this window as well, which is showing register 255. The value over here is simply the offset of main. So this hex 28 means that main is at an offset of hex 28 in memory. It starts out that way. We won't need this, so close that. These are the special registers. These are the general registers. Up here, only 2 have been used so far, so that's why you have only those 2 registers showing. Okay, let me lower this window. I actually will not even need this. I'm going to close the memory window. Okay. Yeah, so let's step. And this should now load. Oh, by the way, $2 starts out as 0. So I'm just using that as a base address. I'm using the fact that $2 will be 0. So it's not something that I did to $2 to register 2. I'm just using this fact. Now, interestingly, $2, so you saw that some fields became red. What the debugger does is every time you step over or step into an instruction and something changes, it gets highlighted in red. Now, as you can see, $2 actually did not change in my instruction. $2 was an input. That's register 2. So why did it get highlighted? And this is interesting, and I don't have the answer to this, but I know, I mean, I don't have the full answer to this, but the reason why it is highlighted is that before main, there's some initialization that the simulator does to call main. Main is run as a kind of subroutine or a function. So in that initialization, $2 is used before we enter main. So it was non-zero before we entered main. But when the program starts, the simulator sets it to 0. So because this happened at this instruction, that's why it's red. But normally, only fields that have changed will be highlighted. So I'm going to find out at some point like what the simulator is doing before it enters main. Right now, I don't know. So what happened here? We took 0, which was in $2 as the base address. We added a 0 to that to get the full address. We're still at 0. We loaded the value that was at address 0 into register 3, and you can see register 3 is now 3. Is this pretty clear? This is really what we did last weekend. So, you know, if you want more details, you can go and look at that video again, or if there's anything that, you know, I can answer, feel free to ask. Yuri says Vim keyboard bindings for, what is this in reference to? Like, which keyboard bindings? For the debugger. Oh, I see. You know, I don't think it's that customizable. Although it is using this open source editor. So the edit window is actually an open source project called Scintilla. I wasn't familiar with it before I used this debugger. I looked at it briefly, so I'm sure that, in fact, I did look at the configuration. It seems to be extremely configurable. So I would not put this past Scintilla's capability. So there may be ways that you can set up Vim key bindings. Okay, so let me just load these things quickly. Another tetra going into register 4, then the third tetra, which is the -5, then these 3 octas, and you can see, you know, all these values get loaded up. Okay, so now we look at our first add, and here we've got an add of register 3 and 4. So register 3 should have a 3, register 4 should have a 7. When we add it, we're going to place the value, the result, in register 9. So let's see that. And that is a hex A, which is indeed 10. Right? So pretty straightforward stuff. I should point out this RL, this will keep changing as long as you use a new register. It basically says this is the number of local registers that you've used so far. And again, this is a concept that we will see later on with MMIX assembly. But right now it doesn't concern us. But it will always be read because of the way I'm using new registers for every instruction. Okay, so here I'm doing a 3 plus and a -5. So the result is going to be negative. And these are tetras, remember, that we had loaded into the registers. So when I run this instruction, I get sign extension, right? The result was negative, a -2, and it got sign extended all the way to the left. And so register 10 now has this -2 in there, in 2's complement. Okay, and here I'm doing, what am I doing here? 2 to the 63 minus 1, which is the largest signed number. I'm adding 1 to it, right? So as a signed value, you know, that's not possible for me to get a valid result. So this will cause overflow. And as we discussed, the overflow is indicated using a bit in the arithmetic status register or RA. It's this bit, hex 40, and you'll see RA down here. This will have the bit set after this add. And the result is in $11. Okay, so that's the overflow that happened. Now, RA has that bit set, so for me to, you know, if this were a real program, I don't want that to remain set, so I want to clear it. And the way you clear one of the, or you set one of the special registers is through this command or this instruction, put. You can't just say, you know, LD something, or you can't access the special registers except via these 2 instructions, put and get. for setting and reading the special registers. So I'm going to clear that, and so you'll see that change to 0. Okay, so that's addition. Now for subtraction. By the way, again, I'm apologizing, but we are going a bit over time, so hopefully for another 10 or 15 minutes. And let's see. Now we have instruction number 10. Oh, here what I'm showing is an example of an addition where you've got one value in a register, but what you want to add is a small value, between 0 and 255. So you can use one of the constants here. You don't have to, set a register and then use it. So here it's just adding 3 and 255. That's this hex FF. I could have said 255 right here. I didn't need to do this, but we should get a result of 258 in register 12. And you can verify that this is indeed 258. Okay, now we do a subtraction of that will give us a negative value in register 13. Fine. Another subtraction. I don't know why I did this one. What's special about this? Maybe I needed this value. I'm not sure. Okay, so now we do a multiplication. 3 times minus 5. So that should give us minus 15 in register 15. And here is register 15. Next instruction, we're again taking that largest signed value and multiplying it by 2, which should cause overflow. So we should see that RA register bit set again. And indeed, that's what happened. What happened to the result in register 16? So you get that in register 16, which is actually a minus 2, as I've written over there. But it is together with overflow. All right, so now I clear RA, and then I do a division. And now we should see a quotient and a remainder. So the quotient will go into register 17. The remainder will go in the special register RR, which is over here. And you can see right now it's 0. And what is the answer going to be? Well, I'm dividing 7 by minus 5. So as real numbers, 7.0 divided by minus 5.0, the answer is minus 1.4. The floor of minus 1.4, which is the integer that is just less than minus 1.4, is minus 2. So that should be the quotient. And then if you take minus 2 times minus 5, you get 10. And then 7 minus 10 should give you the remainder, which is minus 3. Remember, this was the operations that Knuth defined in that mathematical section. So that's going to be the result. Let's see if that's what happens. So we see 2 fields highlighted. RR is this negative number. We can verify that this is indeed minus 3 in 2's complement, and the register that got the quotient is this, which is a minus 2. Any questions so far, or pretty straightforward stuff? Does MMIX store and process doubles using IEEE 754 format? Question from Yuri. I believe it does. I haven't looked at the floating point instructions in detail yet, but I believe that that is what it does. Okay, next instruction, we're going to do a divide by 0. signed divide by 0. So what's going to happen here? I've got a 3 in register 3, and then I've got the immediate, a constant, a decimal 0. So there's no pound sign there. So what is supposed to happen? Dividing by 0 will set the integer divide check bit in RA, which remember I had cleared, so it is 0 right now. It's going to set the destination register to 0. It's going to set the remainder register to the dividend, and it's going to set the divide integer divide check bit, which is hex 80. Arthur had a response to Yuri, I think. Okay, cool. And so let's just verify that is what happens. Oh, by the way, I missed the previous instruction, which was we did get a remainder from the previous division. Now you can't use anything in the special registers directly, as I mentioned. You have to get them into the general register, and then you can use it. So strictly speaking, from an application point of view, you would have to do a get instruction here, get the value from the remainder into, in this case, register 18, and then you can use it. So let's do that. So register 18 became -3. Of course, the remainder register remains the same. It doesn't, set it. To set a special register, you have to use put. So anyway, now let's do the divide by 0, and we get these things that changed in red. Register 19 actually did not change. It was already 0, so I guess that's why it's not highlighted. But it is 0 correctly, and then the remainder register just gets the value of the dividend. And then you can see RA down here became, the bit got set in there. Let's do some unsigned arithmetic. And so these, -5 in memory, it's just bits. So I'm just treating it as unsigned, right? It depends on what instruction you're using to manipulate that data. So treating it as unsigned, this is what should happen. We're adding 7 and -5 treated as unsigned. The result does give us a 2, which is consistent, but again, it's just treating it as unsigned. And 21, instruction 21, I've got a subtraction of unsigned 3 minus 7. So I just wanted to show you what happens when you are treating these things as bits, and that's the result there. Oh, this next one is interesting. That's the himult. So I've got a number in register 3, which is 3, and I've got the -5 in register 5, and I'm going to treat it as unsigned. And what's going to happen is that this will treat it as unsigned. It gives you a product that is bigger than 64 bits. So the result will set the himult register, which is up here. Right now it's 0. And when I do that, it's this value. The upper 64 bits are just 2, and then the lower 64 bits of the result are it's this value. The low 8 bytes of the product, right? So it's this thing. So that's the himult. And again, if I wanted this, the complete result, I would have to get this value from the special register, put it into a general register, and then I can use it. Next one, I'm doing an unsigned division, and here this is pretty straightforward. Nothing really interesting here, just an example of that. The next one is kind of interesting. I'm going to do the reverse of what I did with the high multiplication, which is I constructed a product that would set the high mult register, right? Now, if I wanted to do the reverse, if I wanted to take that 128-bit value and use it in a division, how do I do that? The way you do that is you set the upper half of the dividend in the RD register, the high dividend register. So I'm going to set that to 2 first, because that was my high mult result. So I do that. That becomes a 2. Then in $22, I already have the lower half of the multiplication that I did earlier. So I'm just going to reuse that. I'm going to divide it by 3. So that should give me the number that I multiplied by in the previous instruction. It should give me the -5 unsigned, right? Like over here. So I'm doing the inverse of that. And so what I should see back in $24 should be a -5 unsigned. And is that the case? This is this thing, $24. Is it the same as $5? That's $5 here. Let me make this a little bigger so you can see. So you can compare the two. So this way, you can multiply two big numbers, bigger than 64-bit values, to some extent. And then you can also legitimately do the inverse, which would involve some division. So I think that covers most of, I did have some other instructions in there, but they're, I think, relatively straightforward. And you can look at this file yourself later on. Any questions or comments? Okay, so we again ran out of time for exercises. I think next time we'll definitely allocate more time for exercises. I think by next time you'll also have a little more familiarity with these operations. Most of the exercises really start with the arithmetic instructions, so hopefully you will be able to look at maybe the program and try it out yourself, or just try out the exercises directly, and we'll continue with the remaining instructions. There's not a lot of sections remaining. There's really just the next meetup. Let me actually just show you the agenda for the next meeting. We'll go over immediate constants. I've already kind of shown you how they're used, so there's not really a lot of new stuff there. And then the big one is jumps and branches, because these really form the essential instructions needed for programming control constructs like looping and branching, conditional. So with that, we will have covered everything that we need for basic algorithms and data structures. There's a couple of other things that will be useful. We'll come back to them. Whenever we need them, we'll come back. So we will be coming back to MMIX from time to time, maybe cover another section or two, sort of a mop-up kind of deal. But this is enough for us to get started after the next meetup. And then the fourth meetup on MMIX will simply be just programs that, with input and output and sort of for completion, that will let us work with it in a realistic manner. But Arthur, did you have a comment or question?
Yeah, I put it in the chat. Would it make sense? I don't know what you've planned for the next meeting, but it seems like we didn't get to the relevant exercises this time. Would it make sense to just have next meeting be, let's do some exercises that relate to the arithmetic instructions?
I think it makes a lot of sense, but I would like to cover the new material as well. So I think if we just allocate like 1 hour just for exercises, that should be pretty good. So we'll try to, maybe I can cut down on a number of topics from the first half. So we maybe just do like a couple of sections, spend maybe half an hour on reading, and then we'll just do exercises. Yeah, so I think that's a great idea. Anything else? All right, great. Thank you, folks. So this is where, it's starting to get really interesting in terms of programming. And once we're over this hump, then being able to just simply understand and write simple programs, I think it will be like really, really useful. All right. See you next week.